All right, I wanted to make a video showing my high-level math calcs for how much energy, water, and CO2 emissions are associated with AI data centers. I've recently seen a bunch of different articles that claim AI data centers use, some number of gallons of water per query, or there are X number of kilograms of CO2 emissions due to AI. And basically, the numbers that are cited in all these different articles are kind of all over the place, usually depending on their bias, whether they're very pro AI or very pro environment or climate. And so my goal was to do some calculations myself to come up with my own estimates for how much energy, water, and CO2 emissions are associated with AI data centers. And I was also hoping that this exercise would show what assumptions are implied in all of the different numbers that are cited out there. So with that, let's go ahead and get into some of the back of the napkin math that I've done here, starting with a high-level overview of the data centers and the cooling systems that surround them. So let's start here at the data center itself, which consumes a lot of electricity. So in this made-up example, I'm saying that the data center consumes 26 megawatts of power for doing computations and whatever other AI magic that it can do. I'll say I'm not an expert at AI and data centers itself. My expertise is more in cooling systems and energy systems, but I just know that they consume some amount of electricity, and whatever electricity they consume is converted into heat. So if this consumes 26 megawatts of electric power for doing all the compute that it needs to do, that means 26 megawatts are going to be turned into heat. And that's not able to just build up indefinitely, otherwise the building gets extremely hot and the equipment can't perform. So we have to actively cool the building, or in other words, we have to remove that 26 megawatts of heat somehow. And that's done with the chilled water system. The chilled water system consists of the chiller, chilled water pump, which pumps the cold water, has a cooling tower and a cooling tower water loop or a condenser water loop. Let's start with just the cooling water loop itself. So chilled water comes out of the chiller at, say, 45 degrees or 50 degrees. Depends on the design of the system, but it's relatively cold. It gets pumped into the building where, say, it goes through some coils where some fans blow warm air across it, which cools the air down. And by doing that cooling, the water picks up the heat and it comes back to the chiller warmer than it entered the data center. And it enters the evaporator section of the chiller where it gets cooled down, pumped back into the data center, and then that loop continues forever. So none of that water gets lost in the process. That's a closed loop. The equipment in here doesn't consume water or anything like that. It just dumps its heat into the water. So when we're talking about water consumption by AI data centers, we are not talking about the chilled water loop. We're talking about something else that we'll get into later. So that's the chilled water loop. It's able to produce cold water in the evaporator because there's a separate closed loop going on, which has a refrigerant or freon, whatever you want to call it. So the evaporator section is just a heat exchanger with cold water that runs along the outside of the tubes of some freon tube bundles. And that freon's at a very low pressure and it's very cold, and that's why it's able to produce cold water. So that freon comes out of the evaporator as a gas. It's a low pressure gas. It goes through a compressor, which obviously compresses the gas into a high pressure, high temperature gas where it goes into the condenser section. In the condenser, the freon comes in as a high pressure gas and then it exits as a high pressure liquid. So to go from gas to liquid, it has to lose its heat or reject its heat to this condenser water loop. So the condenser section is basically the reverse of the evaporator. In the condenser, you've got hot gas coming in, and it rejects its heat into the water, and then it exits as a liquid. And on the cooling water loop side for the condenser, you've got cold water coming in, and then warmer water exiting. And that's the reverse of the evaporator because on the freon side, you've got liquid coming in, gas coming out. You've got warm water in, cold water out. So back to the freon loop. You leave the condenser as a high pressure liquid where it goes through some type of expansion valve where it's able to expand into a low pressure liquid. And then that low pressure liquid, because of that expansion process, becomes very cold, where it can go into the evaporator. And then that cycle repeats forever. The compressor is the workhorse of the chiller and the chilled water system. This is by far the biggest power consumer. And the power that compressor consumes is a function of the temperature difference between the condenser section and evaporator section. Now the condenser water loop, like we said, water comes in cold, runs along the outside bundles of the Freon tubes so that it comes out hotter, and then that hotter water goes back to a cooling tower. And obviously, as the name implies, the cooling tower cools the water down so that it can get pumped back into the condenser. And the way the cooling tower cools the water down is it's got a big fan or several fans that suck in outside air, and that air comes in direct contact with the condenser water. So this is not a closed loop, actually. This is an open loop in a lot of cases. The air comes in direct contact with it. This water evaporates into the air, and then moist and warm air exits the cooling tower. And so that evaporation process from the direct contact with the air is what gives it the cooling effect that takes it down from a hot liquid down to a cold liquid. And just for kind of temperature frames of reference here, like I said, this is generally like 45-degree water coming in, say 55-degree return water on the evaporator side or the chilled water side. On the condenser side, it depends on your outdoor air conditions, but typically you can make something like anywhere from 65-degree water to 85-degree water, worst case. And that'll have, it depends on the design as always, but something like a 10-degree temperature difference. So if it comes in at, say, 70 degrees, it's going to come back to the cooling tower at about 80 degrees. And like I said, the air that comes in it evaporates water and absorbs it, and you get moist air out. So since you've got water evaporating and leaving this loop here, you have to make water up to account for that evaporation loss. And this makeup water here to the cooling tower is what we're talking about when we're talking about AI data center water consumption. It's the cooling tower makeup water we're talking about. So just to summarize what we just talked about here, basically, however much electricity the data center consumes for doing computation, effectively that heat is rejected out of the cooling tower. It's just transferred through this chilled water system. And actually, if you're doing 26 megawatts of cooling here, then the heat rejection at the cooling tower is going to be something like 30 megawatts. And the reason for that is because, energy in equals energy out. So you've got to reject not only the heat absorbed by the evaporator, but also the heat generated by the compressor. So whatever energy goes into your compressor also has to be rejected as heat in the condenser and the cooling tower. So we'll talk about kind of how we calculated some of these numbers you see on the screen later. But the first one I wanted to draw attention to is this. This is the makeup water rate. So for a 26 megawatt data center, I've got 134 gallons per minute being made up to the cooling tower. And that is just for the evaporation rate. There's also blowdown that occurs at a cooling tower. So when water's made up to a tower, it's not just pure H2O. There's always some minerals in it. And those minerals kind of build up over time because what's evaporated pretty much is pure H2O. And then any kind of sediment and minerals and things like that get left behind in the basin of the tower. So occasionally, if that builds up too much, you blow it down, which is where you just dump that water and then make up a bunch of fresh water. So that blowdown can account for anywhere from a few percent to 10 to 15% if you don't have a great treatment system. So basically, you could add about 10% to this number realistically. Okay, so that is the water consumption by the cooling tower itself. You've got electricity going to do computations. You've got electricity going to power the cooling system. I've not accounted for lighting or fan energy inside here or anything like that. Just kind of looking at the big users. But if you zoom out to find where this electricity is coming from, it's got to be generated at a power plant most often. So if we zoom out a little bit, for this example, I looked at the grid for Northern Virginia, where there's quite a bit of data center activity, and they've got about 55% of their power on the grid coming from natural gas, roughly 30% from nuclear, and then the remainder from renewables like solar and wind. And with a power plant, I won't go into a whole lot of detail here, but basically, on a high level, power plants have you got fuel that comes in and you combust it. That combustion process is really hot, so you can make steam. If you have steam, you can drive a turbine, and if you can drive a turbine, you can drive a generator to make electricity. That's basically how power plants work. There's a separate discussion about the second law of thermodynamics that explains that you cannot convert 100% of the power from fuel into electricity. So whatever energy is not converted to electricity has to be rejected as heat. And that heat rejection process at the power plant also uses a cooling tower, just like our data center. And that's got to have some makeup water requirement as well. So some analyses will just look at the water required at the data center itself for its cooling tower. And other analyses will zoom out further and look at the water consumed by power plants. And if you're looking at this example here, I mean, just the natural gas plant itself is almost using as much makeup water. And then when we look at the nuclear plant too, which does the same thing, it also has cooling towers. We're looking at 193 GPM at the power plants to generate the electricity, whereas at the data center itself, it's 134 GPM. So when you include the power generation process, we're more than doubling the water consumption that we're saying is associated with this data center. The other thing we look at is carbon footprint. So a natural gas plant will have a carbon footprint associated with it. As it burns fuel, there's 118 pounds of CO2 generated per million BTUs of fuel burned. So for this, the numbers here, that comes out to about 8,000 kilograms an hour. Nuclear plants do not have CO2 emissions, and then renewable plants don't either. So for this scenario where we're saying 55% of the grid power is coming from natural gas, this would be the carbon footprint just for the data center here for this 26 megawatts data center. That's basically the high level here. Next, I will go into my spreadsheet where I'm actually crunching these numbers, and you can see the assumptions that go into this. Before we do that, even though these look very realistic, I'll show you some actual pictures of what we're talking about here. So just a little Google Earth view of a data center in Virginia. I zoomed in and just to see what the cooling towers look like. If you're ever on like a 2D 2D Google Maps kind of view, this is what cooling towers look like from the top. It's basically just a bank of fans is what you'd see. And then depending on what kind of heat load it is and what the weather's like that day, sometimes you'll see some water vapor coming out of them. Now at power plants, this is a street view of a real power plant. This is not just a picture that's demonstrating this. This is an actual Google Street View of a coal-fired power plant. And you can see here, this is the cooling tower for that plant. And it's basically just generating clouds. Like this, the cooling towers at power plants generate tons of water vapor. So that's what that looks like. And then same thing at a nuclear plant. They have that kind of distinct cooling tower shape at nuclear plants. And you can see the water vapor coming off them. A lot of times people think that that's the emission. Those are, the CO2 emissions or the stuff going into the air that makes it dirty air. But this is just water vapor that's coming out. All the dirty stuff at the coal plant is going to be coming out of these big stacks here, which is not visible, ironically. All right, so if you're still with me and wanting to know where these numbers are coming from, here's how I've done these calculations. This is for my made-up data center, where I come up to it being 26 megawatt. I'm saying there are 8 GPUs per server, and I'm making up a number here that there are 5,000 inference servers in this data center. I was just Googling round numbers for average size data centers, and that's what I came up with. So that means there's 40,000 GPUs in total for this particular data center. If each one consumes 650 watts, then our total demand is 26,000 kW or 26 megawatts. For my, and so I guess quick step back. When I'm talking about watts, kilowatts, megawatts, all that, that is a unit of power. And a power is a unit that describes the energy consumption rate. So if we know power, that means we have to know time if we want to come up with an annual energy calculation. So we got to know how many hours per year does it run. And if it's running 24/7, that is 8760 hours a year. These data centers don't really shut down, so we're just going to assume that it's always on. That means if you do kW times hours per year, you get kWh, kilowatt hours. Kilowatt hours are the main unit you use for electricity measurement. That's how you're billed by the power company, so we're using kWh. Now, here's a big assumption that kind of wildly changes our final answers per all of our metrics per prompt. And this is, what is the compute energy per prompt measured in watt hours? If you know how fast that's done, then you can calculate the power that it uses. But we're just looking at the total compute energy per AI prompt that it's answering. I used 0.25. That came from a number talking about Gemini's performance. Doing some more research, I've found that this could be as high as 2 or even 5. So I'm a little bit unsure here on what this number should be. I'm going to plug in 2 for now. But what this changes is the number of prompts per year that you can process. So if you do your watt hours per year divided by watt hours per prompt, you get the total number of prompts that you can process per year. That's what you're changing here, is the total number of prompts per year. Like I said, I'm not a data center nerd. I'm more of a chilled water and energy nerd. So if we get down into these numbers, I can actually back this stuff up better. So let's talk about our chilled water demand. This system's going to have 7,393 tons of cooling, and that is simply the total amount of electricity that's converted into tons of cooling. Tons is a weird unit of power that's used for cooling systems. That unit comes from the amount of energy required to melt a ton of ice in 24 hours, so 2,000 pounds of ice in 24 hours. And that's what, home AC systems are measured in and things like that. So 7,300 tons of cooling is going to be a pretty beastly chilled water system. If that's your cooling rate, then your tower water evaporation rate is going to be 134 GPM, and that comes from this detailed cooling tower analysis here. This is a template that I've used a lot, and it's very complicated. I've got a separate hour-long video describing how this works, so I'm not going to get into it. Basically, you just plug in your outside air conditions and your cooling load, and then this is going to tell you all the performance characteristics of your cooling tower. And so a big factor here is your outside air conditions. Both the temperature and the wet bulb temperature outside are the big variables for cooling tower performance. I got these numbers from annualized weather data for Northern Virginia, where I said this is kind of a data center hub. So I took weighted averages for the year. I basically looked at different temperature clusters and said, okay, for different temperature ranges outside, how many hours per year am I at that temperature? And then when I am at that temperature, what's my average wet bulb temperature and dew point and relative humidity for those hours? And then I took a weighted average for each of those. So that's how I came to say my weighted average conditions are 56 degree dry bulb temperature outside, 50 degree wet bulb. If you're not familiar with wet bulb temperature, what that is if you were to take a regular thermometer and wrap a wet paper towel around the bulb and then swing it around, it's going to measure the wet bulb temperature. So it's basically a measure of how much evaporative cooling you can do in the air. Okay, so anyways, based on this cooling load, this is how much water our tower would evaporate. not accounting for blowdown. Um, we're going to look at the specific power of the chiller. So how much power does it use per ton of cooling? I plugged in zero point 0.6. That's a pretty standard number for the temperature ranges that we're dealing with. Um, the lower the better it is for this number. So the lower it is, that means it takes less power per ton of cooling. And that is going to be a function of, one, the design of the chiller, so how efficient they've designed it to be. But two, it's going to be a function of the temperature difference between this condenser and evaporator section. So for the temperatures that we're dealing with, 0.6 kW per ton is a fair estimate. Based on the total tons of cooling in that kW per ton, our chiller compressor would use about 4.4 megawatts. The chilled water pump, this is just an assumption based on how much pressure it's going to have to generate. It's going to flow about 2.4 GPM per ton if you've got a 10-degree delta T, which is common for chilled water systems. And I'm assuming you've got a 40 PSI delta P through the loop. And then with some pump efficiency estimates, this is roughly going to be the kW used by the chilled water pump. And this is not a huge number compared to the overall power, so I don't think it's worth getting into the weeds of this. Same thing on the condenser water pump section. Condenser water flow is calculated based on a 10-degree delta T through that loop, and the heat rejection that's being calculated. Again, the heat rejection is the chiller power plus the evaporator heat absorbed. So we know condenser water pump power. Cooling tower fan power, that comes from my model here, which we won't dive too deep into, but I'll just say it's all models are wrong, but some are useful, and this one's pretty darn useful. So I trust this fan power calc. With that, we can sum up the power of all the components in our chilled water system to get this number here. And it comes out that that is about 22% of the overall electric power that's being used by the AI servers and whatnot. A sanity check on that, I looked up what that number should be, and I'm seeing that it could be like 30% or as high as 40 even. So I may be being a little bit generous with the efficiency of my chilled water system here, but I think it's reasonable for back of the napkin math here. So with that, I've got my total. If I annualize these are all rates of energy consumption and rates of makeup water. So if I annualize it for this 8760 hours per year, I come up with about 70 million gallons of water that's required to be made up to my cooling tower, and about 49 million kilowatt hours per year of electricity. If we wanted to talk about that in dollars, we assume 10 cents a kilowatt hour. That means it's going to cost us about $5 million a year to just run the cooling system for this data center. So, multiply that by about 5, so 25 million for the power that goes into the data center. So now that we've got annual numbers for our cooling energy and water consumption, we can say, okay, how much total energy does the data center use, which is the cooling water system plus the amount that goes in for compute, 277 million kWh a year. What's our CO2 emissions? Because that's a number that gets cited all over the place. That's varies pretty widely. So let me go into how I calculate this number where I got 73 million kilograms a year. So when you combust natural gas, your emissions rate is going to be about, like I said earlier, 118 pounds per million BTUs burned. And I convert that to kilograms. So it's 53.6 kilograms per MMBTU. Power plants have a wide efficiency range. A pretty good median estimate would be 38%. And they're anywhere from like 30 to 40%. You can get them to be more efficient by doing creative thermodynamic cycles, but I think this is a fair estimate. So if you take this CO2 emission rate for the gas combustion itself and then apply this power plant efficiency, you can get a CO2 emissions rate per kilowatt hour of electricity output. So it's 0.48 kilograms per kWh output at the plant. Now, if this, I would just simply apply this directly to my kWh usage if my entire grid was powered by natural gas plants. But in Virginia, where I'm doing this made up calculation, the grid's about 55% natural gas, about 30% nuclear, and then the remainder is renewables. So if I just take a 55% multiplier on that number, this is my real CO2 emission factor for this grid that I'm looking at. So I apply this factor to this energy usage here to get my annual CO2 emissions rate. And I call them scope 2 emissions here because it's called scope 1 emissions when you directly emit CO2 on your site. Like if you were to burn natural gas on site, that'd be your scope 1 emissions. It's scope 2 emissions when you are using the energy, but the CO2 emissions are generated elsewhere. So that's why I'm calling it scope 2 here. And then I already talked about the annual water consumption. But real quick, what if I'm talking about the total water consumption per year, not just at the data center, but at the data center plus the power plants? It would be that number plus, I'm doing a water calc here. Down here, real quick, what I'm saying is this is how much power is generated at gas and nuclear plants. So we're leaving the renewables out because they don't have any cooling water required. And based on this efficiency, which we can apply to nuclear plants as well, because they're doing the same kind of steam power cycle, that means that my energy input has to be my output divided by my efficiency. And that means that my heat rejection rate is the difference between these two. And that just comes from first law of thermo. Energy in has to equal energy out at steady state. So I convert that to millions of BTUs for my heat rejection rate. And then that allows me to say how many gallons of, or I took how many gallons of water per BTU rejection from my cooling tower model and applied that to my total heat rejection rate for all the power plants here. I guess all that to say is you basically come up with a little bit more than double your water consumption at the data center itself if you're to factor in the water consumed at the power plants that are supplying your data center. So I've got 170 million gallons per year if I'm factoring in power plants as well. All right, so now we get to the numbers that I was really curious about, which is the consumption of all these things per AI prompt that it's generating. So how much energy do I generate per prompt? I got 2.4 watt hours. How much CO2 is emitted? About 0.6 grams of CO2 per prompt. And for my water consumption, I'm getting about 2.3 milliliters per prompt. What's interesting is that if I change this back to the 0.24 number that I had before, my water usage per prompt for just the data center itself, I'm getting what is that? 4074. There's an article that talks about what Sam Altman says. Sam Altman says that they use about same number of zeros, 8 gallons per prompt. So it sounds like Sam Altman's talking about the water usage at the data center itself. When we talk about the power plants as well, like we said, it basically doubles. And that's where you find a discrepancy between what the CEO of an AI company is talking about versus someone who's trying to talk about the detrimental effects on the environment. So that's interesting. And now, since this energy per prompt number can vary pretty wildly, this could be up to 5 even, and that changed my prompts per year number. So my metrics on energy and water per prompt is kind of all over the place. I think maybe a better metric to use would be per per kilowatt hour of data center energy usage. So how much water would I use per data center energy usage? It should be, I think this is a good metric to use. So if I'm looking at just the water on site, maybe 0.25 gallons per kilowatt hour. If I'm looking at the whole picture, maybe 0.6 gallons per kilowatt hour. And I'm not sure how reliable this is because, like my note says here, I'm not including energy consumed by other users that are potentially at the data center, like, the lighting, fans, plug loads, things like that. So take these with a grain of salt. And I guess lastly, the CO2 footprint, that totally depends on how your grid's made up. If you've got a bunch of hydro and solar power, that's going to be super low to nothing, or if you got a bunch of nuclear. Whereas if you got coal power on your grid, then it's going to be much higher. So the point is that these outcomes all depend on the assumptions that go into it. But I think that the process for doing these calculations is useful. And this kind of gives you an idea of maybe what assumptions are used in some of the numbers that are cited out there. So one question that you may have thought of, and a question that I've seen raised out there, is why do we have to use water-cooled chillers at all if we're putting these data centers in water-stressed areas? If we can just eliminate the water usage at the data center, we should be able to cut the total water usage in half, right? Well, the answer is actually a little more nuanced than that, and it's really just a trade-off. And the big trade-off is in this kW per ton here for the chiller. So like I said before, the amount of power consumed by the compressor is a function of the temperature difference in your evaporator and condenser. With a water-cooled chiller, when you're using a cooling tower, you can supply water that's to the condenser that's much colder than the air outside. And that's because it's a function of the wet bulb temperature outside. So if it's 90 degrees outside, you could still make 70-degree water and send that to your condenser. If you've got an air-cooled chiller, your condenser has to be hotter than the outside dry bulb air temperature. So in that example where it's 90 degrees outside with a 70-degree wet bulb, for example, your condenser has to be hotter than 90 degrees outside. Whereas with the water-cooled system, your condenser would have to be hotter than the cooling water that could be supplied to it. So if it's 70-degree wet bulb, say you could make 75-degree chilled water, your condenser would be 80 degrees. And in the air-cooled scenario, where it's 90 degrees outside, your condenser might have to be 110 degrees. So it's just a really big efficiency difference here. That 0.6 kW per ton on average for the water-cooled chiller might be something like 0.9 for the air-cooled chiller. So if I plug that in, this annual chiller energy consumption goes from 49 million up to, I'm going to have to zero out the condenser water pump power and tower fans as well. So we went from 49 million to 62 million. I mean, that's a pretty big jump. But that being said, we would eliminate all the water on site. However, because your cooling system energy increases, the amount of power you got to generate at the power plant offsite increases, so the water consumed at your power plant is going to increase a little bit. So the net effect is you would save water, that's correct, but the energy increase is not only going to make it more expensive for the data center to run, it's also going to increase the CO2 emissions as well. So if we just look at our CO2 emissions per prompt, right now with the air-cooled chiller, we're at 0.67. And if I undo all that and make it a water-cooled system again, we go from 0.67 to 0.64 grams emissions. So your CO2 emissions are better with the water-cooled chiller, but then your water consumption's better with the air-cooled system. So it's a trade-off, really. It depends on the specific scenario you're looking at. So there's not a simple answer to that question of why don't we just use air-cooled chillers everywhere to get rid of the water consumption. So that's interesting. All right, that's all I got. The point of this was not to show that these are the hard and correct numbers. The point was just to walk through the process on how they could potentially be calculated and then compare some of these numbers to some of the articles that I've seen out there. If you see any assumptions that could be corrected or methodologies that could be changed, I would definitely be interested to know that. But I hope you got something out of this or at least found it interesting to follow along. So Thanks for watching if you got this far.